Propositional logic, sometimes called sentential logic, is the most basic formal system in classical logic. It studies the logical relations between propositions, statements that are either true or false, and how more complex sentences can be built from simpler ones using logical connectives. Propositional logic abstracts away from the internal structure of propositions and focuses instead on how whole propositions combine and interact logically. Because of this abstraction, propositional logic is both mathematically precise and widely applicable, forming a foundation for philosophy, mathematics, computer science, linguistics, etc. At its core, propositional logic aims to answer questions such as, what follows logically from what? When is an argument valid? What does it mean for a statement to be logically true or logically false? To answer such questions, propositional logic provides a formal language, precise rules for interpreting that language, and systematic methods for proving logical relations. A proposition is a declarative sentence that is capable of being true or false. Examples include, it is raining, 2 is an even number, and the door is open. Questions, commands, and expressions of emotion are not propositions in this sense because they do not have truth values. In propositional logic, propositions are treated as atomic units, often represented by capital letters such as P, Q, and R. The key idea is that logical validity depends not on the specific content of propositions but on their logical form. For example, the arguments, if it is raining, the ground is wet, it is raining, therefore the ground is wet, and if the alarm is set, the light is on, the alarm is set, therefore the light is on, share the same logical form even though they concern different topics. Propositional logic captures this shared structure. The syntax of propositional logic specifies which expressions count as well-formed formulas. The basic building blocks are usually propositional variables, P, Q, R, etc., logical connectives, negation, not, conjunction, and disjunction, or material implication or the conditional, if-then, and material equivalence or the biconditional, if and only if. Parentheses are used to avoid ambiguity. The syntax is defined recursively. Every propositional variable is a well-formed formula. If A is a well-formed formula, then not A is also a well-formed formula. If A and B are well-formed formulas, then A and B, A or B, if A then B, and A if and only if B are well-formed formulas. Nothing else counts as a formula. This recursive definition ensures that all formulas have a clear structure and that complex formulas are built in a systematic way from simpler ones. While syntax concerns form, semantics concerns meaning. In propositional logic, meaning is given in terms of truth values. Each propositional variable is assigned either true or false. Such an assignment is called a valuation. The truth values of complex formulas are determined by the truth tables of the logical connectives. For example, not A is true if and only if A is false. A and B is true if and only if both A and B are true. A or B is true if and only if at least one of A or B is true. If A then B is true if and only if A is false or B is true. A if and only if B is true if and only if A and B have the same truth value. Using these rules, we can determine the truth value of any propositional formula under any valuation. A sentence of propositional logic is logically true, or a tautology if and only if it is true under every possible valuation. An example is P or not P, which is true regardless of whether P is true or false. A sentence is logically false or a contradiction if and only if it is false under every possible valuation. An example is P and not P, which is false regardless of whether P is true or false. A sentence is logically contingent if and only if it is true under some valuations and false under others, such as P and Q. These distinctions are central to understanding logical necessity and possibility in propositional logic. One formula is a logical consequence of others, a set of premises if, and only if, there is no valuation in which the premises are all true and the conclusion is false. An argument is valid if, and only if, its conclusion is a logical consequence of its premises. Validity depends solely on logical form, not on whether the premises or conclusion are actually true. Propositional logic allows us to rigorously test validity by examining all possible valuations or by using formal proof systems. There are several widely used methods for reasoning and proving results in propositional logic. Truth tables are the most straightforward method. By listing all possible valuations of the propositional variables, we can check whether a formula is logically true or whether an argument is valid. This method is conceptually simple but becomes impractical for formulas with many variables. Natural deduction systems provide rules for deriving conclusions from premises step by step, closely mirroring informal logical reasoning. Common rules include modus ponens, conjunction introduction, and negation elimination. Axiomatic systems start from a small set of axiom schemata and inference rules from which all theorems can be derived. These systems are mathematically elegant but often less intuitive. Semantic tableau and resolution are additional proof methods, often used in automated reasoning and computer science. They aim to show inconsistency or satisfiability by systematically decomposing formulas. Classical propositional logic has several important metalogical properties. It is sound, meaning that everything provable in the system is logically valid. It is complete, meaning that every logically valid formula is provable within the system. It is also decidable, since there is a mechanical procedure, such as truth tables, that can determine whether any given formula is logically valid. These properties make propositional logic a particularly well-behaved and well-understood formal system. Propositional logic provides a precise framework for analyzing reasoning at its most abstract level. By clearly separating syntax from semantics and by offering multiple proof methods, it allows us to study logical structure with rigor and clarity. Although it is limited in expressive power, it cannot, for example, talk about quantification or internal structure of propositions, it remains an important foundation for more advanced logical systems and for the philosophical study of reasoning itself.